Hi, in this lecture I'm going to be discussing the interaction between safety and security. The two are related, and in fact in many of the languages spoken in the European Union they're the same word. Sûreté in French, Sicherheit in German, Seguridad in Spanish. However, when we get a little bit under the surface, we find that although the processes are similar, the technical languages are somewhat different. And what makes it worse is that the language used to discuss safety in software differs from cars to planes to railway signals to toys and other industries. The overall processes are rather similar. We start off with a hazard analysis in safety engineering, and this then drives a safety case. In security engineering, we start off with a threat model, and this drives a security policy. Very often, a hazard analysis has got some aspects of threat in it, and similarly, a threat model looks at some aspects of hazard, because hostile action may cause unsafe things to happen. Also, from the point of view of process, safety and security can either be engineered top-down in a project, if you're building something from scratch, or they can evolve by means of a process as a product evolves. You can have a number of bug fixes are rolled out for an operating system or some other product as time goes on and people find vulnerabilities in it. And similarly, if there are hazards discovered around a product or dangerous behaviors or tricky user interfaces that cause people to make dangerous mistakes, then these can be fixed over time. Do we have an overall concept? Well, the concept of dependability in systems engineering tends to encompass both reliability and security, where reliability is the system's resilience in the face of random hazards, and security is its resilience in the face of adversarial action. And the two are often very strongly correlated in practice, because if you've got software that has been written to high quality standards for safety reasons, then it's less likely to have vulnerabilities. And similarly, if you've built something to be secure, you may often find that it goes a fair bit of the distance in safety as well. But the two are not the same. They are, however, entangled. And what we've got to understand is the relationship between the two, which can sometimes be quite complex. So what's different? The main things that are different are firstly around usability, because safe usability is even more important in safety applications than secure usability is in security applications. You need to have safe defaults, and you need to understand the context of the skills that the operators are going to have. Right? People who drive commercial vehicles for a living have got an extended skill set from ordinary drivers whose skills can range from beginners through capable professional drivers to people on the verge of losing their license because of senescence. The second thing that comes along, which complicates usability, is liability. If you're a company selling a product, such as a medical device or a car, which can put people in harm's way, then if your product injures or kills somebody, then product liability is strict. Even although you may make people click a "don't sue me" button when they fire the software up, there are rules and laws in most countries which cause these "don't sue me" buttons to not work. And in fact, in the European Union, the Product Liability Directive says that somebody who sells a product is liable for death or injury or damage to personal property that it causes. And as a result, where there's a possibility that an equipment failure or an accident was caused by something that was the fault of the equipment or something that was the fault of the person operating it, there's a very strong desire to blame error, to blame pilot error for plane crashes, to blame medical error for things that go wrong with medical equipment. And this gets in the way of safe usability. The next thing is risk, because our risk appetites are very different when there's an adversary present, as I mentioned in the lecture on psychology. Because for millions of years in the ancestral evolutionary environment, our ancestors were at a significant risk of being killed by rivals from other tribes or by being eaten by wild animals, we are very, very sensitive to the presence of adversaries. And if there's even the suspicion that there might be an adversary who has hacked a medical device, then suddenly people will no longer be prepared to tolerate the same levels of risk that they would tolerate if it was just a matter of equipment failure leading to an accident. And finally, what we've got to watch out for is that some of the policies change radically. We discussed multi-level policies, which in the case of confidentiality allow information to flow upwards only, from confidential to secret to top secret, whereas when we've got multi-level safety policies, from safety systems down to operational systems down to billing systems, information can flow downwards only. So if you've got a system that has got both a confidentiality property and a safety property, you may find yourself in a situation where information can't flow at all because the security policy says it should flow in one direction and the safety policy says it should flow in the other direction. So let's look at that in a little bit more detail. In lecture 2, we looked at the Biba model. We discussed it very briefly in passing, where data can flow only down from high integrity to low integrity. And here's a couple of examples. The first is with medical devices, where when the technician from the vendor comes around every 6 months to recalibrate the device, he's got a special smart card or other device that enables him to log on as the administrator and calibrate the device. And when he's finished that, he locks that, and then the doctors and nurses who have to use the device can't interfere with the calibration. So the information flows down from the calibration state to the normal operation state. Our second example is in utilities, because if you're distributing electricity or gas or oil, you typically have 2 or 3 levels of safety in your systems, and the highest integrity level is for your safety systems, the safety systems that would, for example, shut down a nuclear power station if radiation went above a certain level, or that would close down your gas pipeline if you discovered a leak. And these operate entirely independently of any other systems, so that at the next level down, you've got the monitoring and control systems, which respond to the actions of the operators in the control room. And if an operator in the control room does something which causes the radiation in your nuclear reactor to go too high, then the reactor is supposed to close itself down regardless of what Homer Simpson or the other guy in the control room is doing. And then at the next level down again, you may have enterprise apps such as billing, and these in turn should not be able to interfere with operations. So this is the inverse of multi-level confidentiality, where the data flows up from confidential to secret to top secret and never down. As another example, you'll recall shared control. When we talked about banking, for example, we discussed how you typically need 2 managers to authorize a large money transfer. And similarly, in safety-critical systems, we find that some activations require multiple people or specially coordinated actions. Now, the nature of these depends quite closely on the context and on the harms that you're trying to avoid. One extreme example, which I discuss in the book if you want the fuller details, is the management of nuclear weapons. For example, the German Air Force, the Luftwaffe, still has 20 hydrogen bombs, which they get from the Americans as part of NATO arrangements. And the control of these weapons is designed so that they cannot be used unless both the American president and the German chancellor agree that they should be used. And so the arrangement is that the nuclear weapons have unlock codes which can only be unlocked by the US president using codes in a black bag that are carried around close to him at all times. Whereas to actually transport the weapons to their target, the German chancellor has to give orders to the aircrew to climb into their Tornado bombers and then fly the mission. And in this way, it's quite clear and very well understood by both sides that the weapons are under joint command and control. To give a much more mundane example, many years ago in a temporary job, I worked in a printworks, and there we had an industrial guillotine that could be used to guillotine whole reams of paper, whole books at a time. And this thing could cut your hand off in an instant. And so the control for it was that you had a switch at each side, and you had to put your left hand at the left side of the machine and your right hand at the right side of the machine. And this was just to make sure that you wouldn't have a hand in the middle where the guillotine could cut it off. Many examples that we come across in real life are more complex than that, and they involve teamwork. Again, a perhaps typical example here is where a pilot and a co-pilot work together to land a plane in bad weather. And the pilot will be flying the plane down the glide slope on the instrument, staring at the instrument panel, making sure that it stays on course, while the co-pilot will be staring out of the windscreen, waiting until the plane breaks through the clouds and he can see the runway. And when he does see the runway, he'll say, "I have it," and he'll grab the yoke and take control over from the pilot. The reason you do it this way is that otherwise, if the pilot has to fly solo, he has to look at the instruments and then look up to see if the plane has come out of the clouds yet, and then look back down at the instruments. And because he's switching his attention, there's an increased level of hazard, and so he couldn't fly as close to the ground before he made a decision either to land or to go around. And in cases like that, the teamwork has to be very carefully designed, and it has to be very thoroughly trained and very thoroughly practiced. And this brings us to one of the big points in this lecture, that usability is often the big soft spot with safety. Safety usability is an awful lot more complex than it looks because of the interaction with liability on behalf of the equipment manufacturer. In fact, vendors have since forever been trying to blame accidents on user error, right? Because you can either blame the equipment or you can blame the user, and if you blame the equipment, then the equipment vendor ends up getting sued. So that's entirely understandable. But in just about every industry, there has been a long history of tussles between equipment vendors and the public, with the public interest being expressed through regulators who over time make rules to fix stuff. For the first 60 years or so that people were using cars were incredibly dangerous. All through the 1930s or even the 1950s, cars didn't have seat belts, they had lousy brakes, they had poor lights, the roads were awful, the driving tests that people had to do were fairly cursory if they existed at all. People used to drive drunk, and eventually in the 1960s there was a revolt against this, and there was a great push for car safety, which involved the vendors eventually in a whole lot of engineering effort, and now we have better designed cars. We have got anti-lock braking systems. We have got systems in many countries, including Britain, where whenever there's more than a handful of accidents at a road junction, it gets redesigned. They may put in traffic lights, or they may put in street lights or a roundabout or whatever. We've got a big push against drunken driving. Of course, there are still user errors, or things which can be argued are either a user error or a feature of the design of the car or of the road. So in order to mitigate the effects of errors, we provide seat belts, we've got airbags, we've got passenger cages, we've got crumple zones. And do please take a couple of minutes to look at the video on the course webpage on what happens when you arrange a crash between a 1959 and a 2009 Chevrolet. This is a 25-mile-an-hour crash, and as you can see, it impales the driver of the 1959 car on the steering wheel, and if that had been a person rather than a crash dummy, then they would have been killed. The 2009 car, on the other hand, is damaged, but the passenger compartment is intact. The energy is absorbed by the front crumple zone. The energy of the crash dummy coming to a stop is absorbed by the seatbelt and by the airbag. The windscreen isn't even dislodged. So the driver of the 2009 car would have walked away. I'm going to come back to cars later when we talk about autonomy. But now let's go on to our first big case study, which is medical devices. This is the intensive care unit of the hospital in Swansea, where my colleague Harold Thimbleby did a whole lot of studies on infusion pumps. I wonder if you can see how many CPUs, how many computers there are here. Here's a hint. The arrows show the computerized devices, the different pieces of equipment that the doctors and nurses in the intensive care unit have to manage. If you have been in a car crash and you end up attached to a whole load of tubes. And as you can see, there's an awful lot of them. And Harold and his colleagues did a study of this. Harold's dad had died in an accident involving an infusion pump, and one of his students had almost died. So they did an interesting study of it over a number of years, for which Harold was eventually elected an honorary fellow of the Royal College of Physicians. And this is the kind of thing that they found. Here are the infusion pumps in the Swansea Intensive Care Unit. And as you can see, there's a number of different makes from a number of different vendors. And they've all got different user interfaces. And this is a big cause of problems. If you look just at the two pumps called Bodyguard 545, for example, you can see that in one of them, you press 2 to increase the dose, and in the other you press 0 to decrease the dose, whereas in the other it's 5 and 0. So if you're a nurse, you can easily make mistakes. And of course, when mistakes are made and people get killed, the vendors say, sorry, this is user error, this is the nurse's fault. And the nurses then also become victims of this because they're extraordinarily distressed if there's an accident for which they're responsible and a patient comes to harm. So what can be done about this? Well, here are those two pumps in close-up. And you might say, well, you could fix this with standards. But we do have standards. There are international standards on this, and one of these standards says that liters should always be a capital letter rather than a small letter, so it's not confused with a 1. And on the pump on the right-hand side, you can see that the green text conforms with the standard and the yellow text doesn't conform with the standard. So there are clearly issues here, and it has been estimated that approximately as many people are killed by infusion pumps as are killed by motor cars. Something like 2,000 people every year in the UK, and perhaps 40,000 in the USA. And yet there's remarkably little publicity for this, because people who are killed as a result of medication accidents with infusion pumps are usually pretty sick anyway. You know, they're accident victims, they're people recovering from major surgery. And so it's not surprising when they don't make it. And the deaths that arise might be about the 40th or 50th major cause of death in a hospital, so it never becomes a priority for the medical directors to do something about it. And so you've got an environment in which the incentives for safety aren't as strong as they are with cars. So what can be done about it? Well, somehow you've got to fix the incentives. Safety usability gets ignored because the incentives are wrong, and this has been the case for many years. But one of the interesting things that happened is that in 2015, a professor at the University of Michigan, Kevin Fu, demonstrated that the Hospira Symbic infusion pump could be hacked remotely over Wi-Fi, and in fact you could go in via this infusion pump and get into the hospital network. And this led the FDA, the Food and Drugs Administration in the USA, which regulates medical devices, to panic and to blacklist this infusion pump. There were dozens of other pumps which were unsafe for various reasons around their user interface that the FDA wasn't prepared to do anything about. But the mere possibility of tampering by some hostile person in the car park with a radio was enough to get them off their behinds and do something. 2 years later, there was something that the industry couldn't ignore. There was a recall of 450,000 pacemakers from a company called St. Jude, because other security researchers pointed out that the St. Jude pacemaker could also be taken over via the RF channel. And so it would be possible, for example, to target someone who used a pacemaker and take over their pacemaker and perhaps kill them. There was even a movie made where the plot was that foreign agents conspired to kill the vice president of the USA who was using a pacemaker. And when Dick Cheney was vice president of the USA, he did have a pacemaker, so this was perhaps a realistic plot. And having to recall all these pacemakers costs real money, because to change a pacemaker, it's a local surgery procedure. The pacemaker is typically implanted under your shoulder blade, and so you've got to go into hospital, and the surgeon's got to cut you open and fish out the old one and plug in a new one and sew you up again. And they've got to have all the equipment there to revive you in case you go into a heart attack while you're under. So it's a process that costs several $1,000s per patient with some surgical risk. And so the cost of recalling all these pacemakers was in the billions. So finally, in 2021, President Biden appointed Kevin Fu to the FDA. So at last, because of a security vulnerability, we begin to see some action on the safety usability front. In the European Union, at the same time, we've seen some action too. The medical device directives have been revised, and from 2021, people selling medical devices in the European Union have to do post-market surveillance so that they can observe what's going wrong with devices and keep some decent statistics of accidents and casualties. They've got to have a risk management plan and ergonomic design. And one of the things that drove this through was the requirement for security, because one regulation states for devices that incorporate software, the software shall be developed in accordance with the state of the art, taking into account the principles of development life cycle, risk management, including information security, verification, and validation. Okay, so we're making progress at the task of seeing to it that medical devices can't be hacked by somebody sitting outside your house in a grey van with a radio. And we've also seen progress in the form of staffing up the FDA, because over the past 6 or 7 years, the FDA technical staff who are involved in scrutinizing devices before they're approved has increased from 2 engineers to over 100 engineers. So there is serious progress there because of the security scares. But progress is still a long, hard slog, because you still have all these infusion pumps on the market with incompatible user interfaces. And of course, every vendor says, well, why should I change my user interface to be the same as Fred's? He should change his to be the same as mine. If you've got 2 devices on the market with incompatible interfaces, that may not save you, but still it's a real problem. And the underlying problem is an entrenched cartel of suppliers. The people who make these devices have bought up their competitors until there's only a few big firms left, and they've got an awful lot of lobbying clout. And in the absence of something like a security scare, if the FDA threatens to remove the certification from a medical device, then the congressman for that medical device maker's district will be phoning up the director of the FDA to talk about his budget. And we see the same kind of problems with other medical equipment. Fatal accidents with medical accelerators, particle accelerators and powerful X-ray machines have been reported since the mid-1980s. And you may have seen the Therac 25 incident mentioned in your software engineering courses. If not, Google it. It's one of the classic stories that was investigated by Nancy Leveson in the 1980s when it happened. But the problem is that these incidents are still happening, because regulating safety in the real world, where you've got lots of deployed products, where you've got billions of dollars of investment riding on them, and you've got all the imperfections of politics in the real world, doing that is actually seriously hard. How we maintain a safety case, or for that matter, a security assurance level, is a big deal in many sectors. And the economics of this are fairly straightforward. Vendors prefer to front-load certification. They want to put all the effort into producing a device, a car, an airplane, a medical device, which is certified safe or certified secure, and then just sell it forever afterwards. And if you put all the effort into the upfront certification, then the cost of that will help deter new market entrants. So with luck, there will be less competition. They tend, however, to dislike recalls, which are expensive. And as we get software into more and more things, then there's more and more patching involved in maintaining both safety and security. And in some sectors, this is causing real stress. Now, in the case of medical devices, the pressure point here for regulators is post-market surveillance. And we're seeing similar patterns with cars, with household goods, and even with aircraft. In fact, the worst ever software failure that we know of was the failure of the Boeing 737 MAX, where 2 aircraft crashed because of a new flight control system that was not fit for purpose, because Boeing tried to stretch systems that had been developed for previous versions of the 737 into a new version of the 737, which had bigger engines and therefore had different handling characteristics. We don't have time to go into that story here, but it's certainly worth studying if you're interested in software and safety. Now, the systemics of the maintenance of safety and security, which we could call sustainability, we'll deal with in the following lecture. For now, let's get on to our next case study, which is autonomous vehicles. Now, autonomous vehicles perhaps get their beginning when Sperry demonstrated an autopilot for aircraft in 1914, just before the First World War. And they have been around for years and years and years in fairly primitive forms. The first decisive use of remotely piloted vehicles in conflict was in a war between Israel and Syria in 1982, when the Israelis were able to send autonomous vehicles over the Syrian air defenses to draw fire from the Syrian air defense batteries, and then they were able to use other vehicles to take these defense batteries out. That got serious interest from the world's defense establishments into remotely piloted vehicles, and we thereafter saw the deployment at scale of cruise missiles, air-to-ground and sea-to-ground missiles with ranges of hundreds to thousands of miles in the armed forces of a number of countries. The next big step was in 2004, when the US Defense Department's Advanced Research Projects Agency issued a challenge. The US troops, and indeed UK troops, were taking significant casualties in Afghanistan from improvised explosive devices. And so what DARPA wanted to do was to get an autonomous vehicle which would be able to take supplies to and from outposts in Afghanistan and in Iraq. And in order to spur firms on to develop this, they offered $1 million to the first team who could build an autonomous vehicle which would cover a pre-specified track of 149 miles through the Mojave Desert. That year, a number of teams competed, but no one was able to complete the drive. And the following year, when they doubled the prize money to $2 million, the winner was a robot car called Stanley from the Stanford University's robotics department. And that certainly got people to wake up and take note. And in 2009, Google basically hired the whole team to work on self-driving cars and announced in 2010 that this was going to be a moonshot project, that they would spend $100 million on going all the way to a self-driving car, while previously the car industry had been trying to go there by means of a number of incremental steps. Google tried to do it big bang. The first company to field a product that was announced as self-driving was Tesla, with its Autopilot system in 2014. And before we discuss this, we'd better make clear what we mean by autonomy. Now, the industry now recognizes 5 levels of autonomy. These levels have been agreed by the safety authorities in the USA and in Europe, and also by the insurance industry, and they are as follows. Level 1 is where the software controls either the steering or the speed. So an example here is adaptive cruise control, which would let you set your car to go at 70 miles an hour on the motorway, but to slow down if there's a car in front. And this is now fairly widespread, and it's great for driving on the motorway in traffic. If you hit traffic, you don't have to constantly use the accelerator and brake to slow down and speed up. The car stays about 50 yards behind the car in front if you're going at 50 miles an hour, and about 70 yards behind the car in front if you're doing 70 miles an hour, and so on and so forth. So that's now widely in use. Level 2 is what you find with the the advanced driver assistance systems, the ADAS systems, that you get with some top-range cars nowadays. Here the software controls the steering and the speed, but the driver has to take over at zero notice if the software fails. This is also what happens with the typical autopilot in a light plane. So with such vehicles, what you've got is the same kind of adaptive cruise control that we've had for a decade or so, plus also there's an automatic lane keeping system with little cameras typically mounted in your wing mirrors, which mean that you can stay in lane on the motorway. However, if the car gets confused, it rings a bell and you must be prepared to take over at zero notice. And this is one of the big problems, as we will discuss in a minute. Level 3 means that the software is also monitoring the environment, but assumes that the human's available as fallback and can grab the wheel within a few seconds if it sounds an alarm. Level 4 drives the car without assuming that a human's available to intervene, and if it gets confused, it stops the car safely at the side of the road. This is the goal for many teams that are developing advanced driver assistance systems, but none of them are there yet. And finally, level 5 is the science fiction future, where software can do everything a human can, where one of Asimov's robots climbs into a car, starts up the engine, grabs the steering wheel, drives off, and does everything that a human being can. So what do we have? Well, the automated or advanced driver assistance systems, the ADAS systems, operate at levels 1 or 2. And if the computer gets confused, it just rings a bell and then suddenly you're on your own. This is similar to in an airplane, where the autopilot will steer the plane and keep us at the right level and speed, but you're entirely responsible for looking out for other aircraft, for using the radio to talk to air traffic control, and so on and so forth. And what goes wrong is that drivers assume that autopilot means level 4, when in fact they're getting level 2. And there have been all sorts of accidents where people in Teslas, for example, have set up a laptop on the passenger seat and they're watching a movie while they're going along the motorway, and then a lorry pulls out in front of them and they smack into it and they get killed. The same thing happens even with some demonstrations of robo-taxis by Uber and other vendors, where you had a safety driver in the taxi, and yet the safety driver turned out to be watching a movie on their phone at the time the crash happened. Now, this is a fascinating study, because on the one hand, you'd think that even level 2 would help. And the reason for this is that falling asleep at the wheel causes 20% of road traffic accidents, including 30% of fatal road traffic accidents. And in motorway driving, half of all fatal accidents are due to people falling asleep at the wheel. And the reason that these tend to be more deadly is that if you don't brake in advance of hitting a tree, then you may hit it at 50 or 60 miles an hour, at which you'll be killed. But if you were awake, or at least wakened up in the last few seconds before impact and stamped on the brakes, then you could maybe get the speed down to 20 or 30 miles an hour and you'd have been able to walk away from that. So here's the big question. If automatic cruise control plus automatic lane keeping plus automatic emergency braking would prevent half of these accidents, then surely death should fall. Now, the surprising thing in terms of what we get is that accidents aren't down. Now, this gets complex because last year, Tesla claimed that there were fewer fatal accidents when its so-called autopilot was engaged on the freeway than when it wasn't engaged. And initially, they persuaded the National Highways Transportation Safety Administration in the USA that this was the case. And then what happened is that some of Tesla's competitors analyzed their data and found that, in fact, there were more fatal accidents when autopilot was engaged. And one of the things that the community's been doing over the last year is investigating why this is the case. And there's a number of explanations have been put forward. The first, which we mentioned in our psychology lecture, is the risk thermostat, the fact that people adapt to a perceived reduction in risk. People driving a Volvo may drive faster than when driving a Peugeot. And similarly, if people get into a Tesla, which they're assured has an autopilot, they may believe that this means they can take less care, even when that isn't the case. The second has to do with affordances, which we also discussed in psychology. The way people behave with a technology depends on the ways in which the technology is usable by them. And if you're driving a normal car along the motorway and you're working the accelerator and the brake and the steering wheel and perhaps even the gear stick, then you're definitely in the loop, you're engaged, you're doing stuff, and so you pay attention. However, once you have got adaptive cruise control and automatic lane keeping, there's really not very much to do, and so people relax. The third theory is that it's down to industry marketing, and in particular, insurance companies are kind of annoyed that Tesla calls its ADAS system an autopilot, because most people don't understand that if you're flying a light plane with an autopilot, you've got to keep on paying attention. They assume that if the autopilot is on, then the pilot can go for a wee or eat his lunch or chat up the stewardess or whatever. This isn't the case, but people don't understand that. And so the insurance industry really wants Tesla to stop calling its ADAS system an autopilot. And recently, a fourth thing has come up, which is that in Tesla, as in a number of other cars, the autopilot switches itself off when it gets confused. And this appears to have been poisoning the accident data, which Tesla was giving to NHTSA, because typically, just before a fatal accident, the autopilot would have got confused, and it would have then run the gong and said to the driver, "You take over now, I don't know what's going on." And then smack, you go into the back of a lorry and get killed. And that fatal accident is then recorded as an accident which was the human's fault rather than the autopilot's fault, and thus something that has to be paid for by the driver's insurance company rather than by Tesla and their insurance company. And these liability issues are one of the things that systematically bias and cause problems for the whole world of safety, as well as indeed the world of security. So why is autonomy hard? Well, one of the things that people pointed out a decade ago at the start of this whole project is that it takes about 8 seconds for a commercial pilot to assume control after an autopilot failure. And there have been a number of well-documented plane crashes due to this. For example, there was an Air France flight flying from Paris to Rio, where the autopilot failed over the South Atlantic. And in the seconds that it took the pilots to grab hold of the yoke, the aircraft went into a high-speed stall from which they couldn't recover. So this is known to be a problem in commercial aviation. And that's despite the fact that on the deck of a commercial aircraft, there will be at least one trained, sober, alert pilot who has got thousands of hours of experience and who's ready to assume control on zero notice. When you start dealing with the population of drivers of cars, the population is much more diverse. It includes learner drivers, it includes drunk drivers, it includes old people in the early stages of dementia who really should have stopped driving but who haven't been told to yet by their doctors. It includes, as we've said, drivers who may be watching a movie, or safety drivers in taxis who may be watching a movie because they don't understand the limitations of an ADAS system. And so if it's bad for planes, it's going to be even worse for autonomous vehicles. And in fact, Volvo has taken the view that they're not going to describe any of their ADAS systems as self-driving or autonomous until they get to level 4 and until they are certain that the car can stop itself safely at the side of the road if it gets confused. And that's something towards which the industry is currently working. But it's really, really hard. Now, when you talk to the people who are trying to do the certification for this, one of the problems you find is that one standard for level 4 the Singaporean standard as it happens, says that the car must come to a stop in the same lane when it gets confused. And this turns out to be not testable for the simple reason that cars often get confused about the lane. For example, if you're going through roadworks, then the lane that's painted on the tarmac may be superseded by a lane from a line of traffic cones. And also, if there have been recent roadworks, or if there's a traffic diversion with temporary lanes on a motorway, you may find that the existing lane markings have been painted over with black paint, and that can shine, particularly if the road is wet and there's reflection from streetlights or from the moon. And this means that cars get really confused about where the lane is, and therefore there's no way you can figure out how you're even going to test the standard which says that the car has to come to a safe stop in the same lane. Another set of problems is the difficulty that self-driving cars have of dealing with other drivers, particularly anything that involves manners or courtesy or giving way to other vehicles. And the classic problem with which Google has been wrestling in its self-driving car trials in California and elsewhere is turning across traffic. Because if you're going to make a right turn on British roads or a left turn on American roads so that you're turning across another lane of traffic, then what you're forever doing is, waving to a car that's approaching and exchanging little nods and winks and tacitly negotiating who's going to go first. Robots can't do that. And as a result, it takes self-driving cars forever to turn across traffic, which makes the cars behind them annoyed, and they hoot and they try and overtake in non-standard and even dangerous ways. Also, if you're trying to make your way down a suburban street that's got cars parked on either side, then you end up having to implicitly negotiate who goes first with cars coming the other direction. And that's also something that at present robot cars are simply incapable of doing. We just don't understand how to deal with manners using machine learning systems. In order to drill down even further, let's look at the act of braking. Now, in a typical self-driving car, there are basically three braking systems. Firstly, there's adaptive cruise control, which is more a throttle control than a brake control, although it can engage the brakes when it has to. And this roughly says that if you're traveling at n miles per hour, you should stay n yards from the car in front. And the implementation of this is radar. However, for this to work on roads that aren't motorways, right, if you've got cars coming in the other direction, then if you're going at 50 miles an hour and the car in the other direction is coming at 50, that means a closing speed of 100. So do you panic and slam on the brakes? Well, no, what you do is you tune your radar so that it will only see things in a certain velocity gate, say, for example, at velocities within 10 miles an hour of your own, and at a certain distance, say from 25 yards or 30 yards ahead of your car to 200 yards ahead of your car. So what happens if a car squeezes in just in front of you? Well, the answer is that you don't see it. So this is a known existing problem with things that we've had deployed for over 10 years now. The second type of braking system you've got is emergency brake assist, which is designed to help the driver do an emergency stop. So most people, when they stop a car, only brake at about 0.3 of a G, but the typical car will brake at about 1 G, and that makes a big difference if a child or a dog has run out in front of you. And so what a modern car will typically do is that if it detects that you've moved your foot from the accelerator to the brake in less than 300 milliseconds and then applied 2 kilograms or more of braking force, then it will do a hard stop for you, a full-on deployment of the ABS. And you'll come to a stop so hard that you'll find yourself hanging in your seatbelt. Now, I once did this in my car by accident, and it can be pretty scary. So the question there is, do you save more front-end crashes than you cause rear-end crashes? And now we've got the statistics in from the insurance company. The answer is yes. And then there's automatic emergency braking, which has only been around for the past 5 years or so, and mostly just in luxury vehicles. And this is deployed if needed. And the idea here is that the car's forward-looking cameras and perhaps LiDAR as well, look for dogs or kids or whatever that run out in front of the car, and if need be, they will then brake. The implementation is usually video, that is machine vision, rather than LiDAR. But this has been one of the big sources of trouble for people designing autonomous vehicles. It's really tricky to do, particularly in town traffic. A number of very bright teams have worked on it very hard for 4 or 5 years now. And the big problem is that you very often have too many false alarms. And so in a number of the cases in America where Teslas and other ADAS-equipped vehicles have run over pedestrians or cyclists, it's turned out that the automatic emergency braking system has been switched off simply in order not to be too annoying to the driver. Now, when we get to the interaction between safety and security, the big question here is, what if one of these systems can be hacked? Right? Because there is a trade-off between front-end crashes and rear-end crashes, and if you could somehow send out a signal to all the Mercedes cars in the world saying you must do an immediate emergency brake assist stop, so that all the Mercedes cars in the world suddenly braked at 1G, then there would be an awful lot of rear-end collisions and a fair number of people would be killed. So how do you prevent any kind of hostile adversarial deployment of systems like this? Well, there have been academic demonstrations of car hacking going back, over a decade now, but these only burst through into public consciousness in 2015 when two ex-NSA guys, Charlie Miller and Chris Velishek, hacked a Jeep Cherokee remotely using the mobile network. You see, each of these Jeeps had a mobile phone, and they were all on a Sprint network. And you could go through the IP addresses on the network and then interrogate the cars one after another about their GPS location until you found the car that you wanted to hack. And so what they did was that they got a car that was being driven by a journalist who was writing a story about their hack, and they slowed it down and slowed it down and slowed it down until the traffic behind the trucks were all honking and tooting and pulling out to overtake. And then they ran it off the road, as you see in the picture. And they did that basically by using the parking steering assist, the mechanism in the car that you use to back into a parking space. And this was such a vivid demonstration of the risks of what could happen to modern cars over the air that all of a sudden everybody cared very, very much about this. And Chrysler had to recall over 1 million vehicles for a software fix, which cost them over $1 billion. Second example of how cars get hacked goes back to the Volkswagen emissions scandal. The chap on the left is the former CEO of Volkswagen, who ended up being fired and prosecuted after it turned out that he had arranged for Volkswagen diesel models to detect when they were undergoing an emissions test and then to make nice and run in such a way that their emissions were really, really low. The rest of the time, their emissions, particularly the nitrogen emissions, which cause asthma and other diseases, shot up. To keep the emissions down, you have to keep on putting blue spec in the car, but drivers find that annoying and it impacts performance in other ways. And so Volkswagen, and indeed most of the other car vendors, had just hacked this by detecting when a test happened and cheating on it. And when this came out, Volkswagen's share price tanked. That's the graph that you can see on the right. And the consequences for the industry were dire. All of the big car vendors are now being sued because they were all basically at it one way or another, and lawyers are now suing them on behalf of millions of users to get compensation. So the important thing to learn from this is that the enemies aren't just outsiders. The enemies are also insiders, and the enemies, or the opponents if you prefer to call them that, can include the chief executives of the car companies themselves. And this is an interesting example of the insider threat. So what do we expect from security threats in the future? Well, one of the things that we're working on in our research, this is funded by Bosch, which is one of the main vendors of machine vision systems for cars, is the fact that at present, machine vision systems in cars are significantly detuned because of the possibility of attacks on them using things called adversarial samples. You may have come across in your machine learning lectures the fact that vision systems nowadays are all done using deep neural networks, because for the past 10 years or so, these have been so much better than all the systems that we used to use in the old days. However, deep neural networks are very vulnerable to attacks using what are called adversarial samples, little tweaks that you can find using gradient descent methods, which will cause things to be misrecognized. So you can come up with little hacks that will cause a car to misrecognize a 30-mile-an-hour sign as a 60-mile-an-hour sign. And this could actually result in an attack. For example, those researchers in Israel have demonstrated how you could project a confusing image onto a motorway bridge and potentially cause a car crash. Now, these are probably not significant attacks in real life, because if you want to cause a crash in a passing car, you just go to roadworks and you kick the cones into the hole in the road, and the next car coming along is going to crash. Do we worry about that? No, we don't particularly. Or you could stand on a bridge and you could drop a brick through the windscreen of a passing car. Has it been done? Yeah, it was done once during the miners' strike back in the 80s, and the guys who did it were sent to jail for life. But do we worry about it as a systematic security threat? No, we don't. So what can you do about that? Well, what we've been working on is trying to figure out how you provide better alarms so that a machine learning system can have some situational awareness and understand when it's under attack. And when that happens, then you can slow down, or you can demand that the human driver take control, or whatever. This is one of the things that we're learning from practice. We're probably going to have to do as we deploy machine learning components into systems that have got safety and security requirements in the real world. The first two cases that I discussed in this lecture, medical devices and cars, are fairly typical of the kind of engineering problem you may be tackling once you start in your professional life, where you have got some safety goals and some security goals, and you have to understand them well, figure out the tensions between them, figure out the priorities, and figure out how you meet these goals using available mechanisms. My third case study is a little bit more difficult, and it's one that we ignored, I'm afraid, in the security world until about 5 years ago. It's intimate partner abuse. An awful lot of the nastier crimes that we see, with kids being killed and so on, are things that happen in families that have become dysfunctional. And the typical thing that we're worried about here is intimate partner abuse. Now, this is experienced by 27% of women and 11% of men in the UK at some time in their lives. So it largely, but not exclusively, has women as victims. It also has children as victims, and when children become victims of abuse, then they very often are more likely to go on to become criminals in later life. So this is a serious social concern. So imagine that you're a woman who is in a relationship with a man who has become violent and abusive and controlling. And your process of escaping from this relationship will typically go through 3 phases. First, there's the physical control phase, where the abuser has got access to your devices, your phone, your tablet, your laptop, if any, your accounts on Gmail and Facebook, because of course your husband or boyfriend or whatever will know what your passwords are. He'll have bullied or intimidated you into handing these passwords over. So you can go into your Gmail and see who you're corresponding with. You must assume that he's jealous and controlling, and that he could do you harm by, for example, posting abusive things in your name on your Facebook account. So after you've decided that you've had enough of this abuse, you plan your escape. You figure out how you're going to get away with your kids and find a new home and a new job and so on. Now, on average, this takes 7 attempts. And it's a very, very hard thing to do, particularly if you don't have any resources, if you don't have any money. And in many cases of intimate partner abuse, the woman may not have an income and may be dependent on the controlling partner, to feed their kids. So this makes it even more difficult. Now, assuming that you manage to escape, you've then got the life apart phase, where harassment may be an issue. Your ex-husband or ex-partner may want to turn up and beat you up or snatch the kids or cause other problems, and you may have to change your career. It may have to restrict children's online activity in case the abuser turns up. You may even get court orders to try and prohibit the abuser from coming within several hundred yards of your house. He may ignore the court orders and come and try and attack you anyway, so you may have significant physical security concerns. And you'll also have electronic security concerns, because what if he tracks you down through your online presence? Now, about 5 years ago, a number of people started to realize that much of the standard security advice that we give everybody is unhelpful in such cases, or even plain wrong. So imagine that you're just about to make your escape, and you want to make sure that you can't be tracked through your online account. Well, the standard advice would be, if somebody else has got access to your account, then change your password. But if you're still living in the abuser's house, do you even dare to try to do that? Because if you change your password on your Gmail account and your husband finds he can't get into it to find out who you've been talking to, then he's just going to come and beat you up. He would then reset your account, because of course he can answer your recovery questions. And if your recovery mobile phone number is his mobile phone, or even if it's your mobile phone and he can just snatch it out of your hand and use it, then you don't have a means of recovering your account. So one of the things that you have to think about is whether you can afford to buy another phone. And if so, where would you charge it? Where would you keep it? Would you have to plan your escape using a PC at a library or at work? Then you have to figure out how you can use social media if your circle of friends is common with the abuser. This is a particular problem for victims who are self-employed and who use Facebook to get work in. Suppose you're a self-employed hairdresser and you get your work from your 200 friends on Facebook. And if 150 of these are also your husband's friends, then you've got a problem. You may end up having to build a life entirely from scratch, or even find an entirely new career or profession when you make your new home in another town. And so once the enormity of these problems began to sink home, there's a number of research groups started asking what you should do as a designer to at least make things no worse for abuse survivors. And there's an interesting paper by Sunny Consalvo and her team at Google, who have been looking at this for about 5 years now. And I encourage you to read it. And the big takeaway message here is that here the enemy is an insider, in the sense that the enemy is you, right? If you're a woman trying to make an escape from an abusive husband, and your husband knows your Gmail account and knows your Facebook password, and has physical access to your phone because he can grab it from your fingers and look at what's on it, then the enemy is you some of the time. And how on earth can you design systems to provide the possibility of security when they may be taken over at any time by the enemy? Well, there's a number of things that Sunny Consalvo and our colleagues come up with. The first is a focus on usability, which again, we've seen in the case of medical devices, and we've seen in the case of cars, but it comes up here again. And you have to focus on usability, particularly at times of high stress and high risk. And to understand what these times are, you've got to speak to a lot of survivors and sit down with them, have tea and coffee with them, and listen to their life stories and figure out what worked and what didn't work, and what led to them being beaten up and what actually helped them when they made their final successful escape attempt. Some of the things that have been learned in detailed design terms are as follows. First, you should allow users to have multiple accounts rather than trying to herd everybody into a single account, as some big tech firms do, because having multiple accounts can be an absolute lifesaver. The second is that you have to enable the user to have control over the visibility of their actions. Someone reviewing your history should not be able to tell if you deleted anything. But on the other hand, you should still be able to capture evidence, because if you're a woman making an escape from an abusive husband with your kids, then in a year or two you're going to end up in a family court and your husband will be demanding access to the kids. And if your claim is he shouldn't have access to the kids because he used to beat them or even abuse them sexually, then you're going to have evidence of that you can show to the family court in due course. And how do you capture evidence while at the same time not making it obvious to your husband, who also has access to your accounts, that you're doing that? And so the sort of things that you do include pushing incognito mode, so that people can do things that don't leave a record, and they can do so in an easily controllable way that everybody understands. You need unusual activity notifications so that it's difficult for the opponent to observe you without being observed themselves. And it's also useful to have two-factor authentication so that you have some means of making a clean break from someone who knows quite an awful lot of your secrets. If you can somehow see to it that you can get yourself a new phone and use that new phone to provide the second factor, then that provides you a means whereby you can break away. For further details, I recommend that you read the Consolvo paper. So to sum up, what is the relationship between safety and security? Well, safety and security have got an awful lot in common, and in fact they're the same word in many of the languages that are spoken in Europe. They very often overlap, they get entangled, and sometimes they reinforce each other, and occasionally they conflict. And this isn't just a conflict, of course, between safety and security. You can have a conflict between different safety goals, you can have a conflict between different security goals, and you can have a conflict between the safety and security goals of different players in the system, because the interests of the car vendor, the car driver, are not the same. The interests of the big tech company, its advertisers and its users are not the same, and you really have to understand who the various players are and what they're trying to achieve. In order to do this, you need to study the context with real care. You have to understand the hazards against which you're trying to provide safety and the threats against which you're trying to provide security in detail. You have to ask safety for whom and security for whom, as well as safety from what and security for what. And you also need to think methodically about personal and institutional incentives. So economics matters, usability matters, and understanding the context matters to an enormous extent. And in our next couple of lectures, we'll be looking at the assurance aspects and about the governance aspects, and the kind of conceptual and governance mechanisms that we can use to get a handle on all the various conflicts between different security goals, safety goals, and the interests of different parties.